atomic models. We are back onto the stage of atomic models, and here the first atomic model was proposed by Sir J.J. Thomson. So, yeah, so coming to our J.J. Thomson's atomic model. The plus point of this model is that it explains electrical neutrality. In John Dalton's model, it was just a solid sphere that didn't even introduce the concept of charges, but Thomson's atomic model's plus point is it introduced charges, and it didn't only introduce charge, but it also explained its electrical stability. So, what exactly was Plum pudding model? In terms of Indian conditions, you can say it has to be resembling watermelon model. So J.J. Thomson have considered atom to be a positive sphere where negative charges are embedded. So as per Thomson's atomic model, the positive, the beneficial point is it explains electrical neutrality or stability. Uh, so the positive point is that it explains electrical neutrality and uh, electrical neutrality or stability, but the negative drawback of this model is unfortunately couldn't satisfy experimental studies. Now, since the positives and negatives, since we have come across the positives and negatives, Thomson's atomic model gave a clear-cut representation of electrical stability, but failed to prove the future experiments. When after a couple of like after a couple of years passed, scientists have sit on Thomson's atomic model. They have thought about his model. They have carried out some experiments, and unfortunately, those experiments couldn't prove it. And Thomson's atomic model have to be discarded. Now, moving to the next, the most curious part, the most interesting part of this chapter is Rutherford's atomic model. This led to the this played a major role in today's atomic model, that is the present atomic model, and uh, he is the student of Sir J.J. Thomson. So Rutherford's gold foil experiment, what exactly Rutherford did? Rutherford have taken an alpha particle source and bombarded alpha particles continuously onto the gold foil, and that continuous bombardment of gold foil led to some of the most important observations. First thing, let us understand why Rutherford chose this particular experiment to be conducted in this particular way. So, first and the foremost thing that we should understand is cathode ray particles were discovered, anode ray particles were discovered. Now, Rutherford wanted to find out the structure of atom. So for that, what he did, he took thinnest possible metal piece and he have bombarded it so that he can see what would be the changes or what would be the outcomes of a charged particle being bombarded on an atom that consists of different types of charges. More importantly, in Rutherford's era, there was no neutron. Rutherford's experiment was conducted in 1911. So in and discovery of neutrons was 1932. So by the time Rutherford was carrying out his experiments, the concept of neutrons were not even close. Clear till now? I hope you are clear. Now, getting before getting into this, let me explain you that Rutherford, to study down the atom's model, he decided to bombard charged particles on atom so that he can get a clarity. So Thomson said that atom is a sphere of positive charge. So if it is a sphere of positive charge, then when helium particles or alpha particles are being bombarded, then there should be deflection, and maybe through that way he could prove his teacher's hypothesis or his teacher's atomic model. So to prove his teacher's atomic model, to find out the correct accurate atomic model, he have carried out this experiment. In this experiment, he have deliberately choose the use of gold foil, and this use of gold foil was deliberate because of its primary reason that gold foil is highly malleable. And when I say it is highly malleable, it means it can be easily drawn into sheets. And if you're wondering how thin is this exactly, it is one layer of atom thin. So it was that thin, just a single layer of atom. It was beaten into that much of thinness. And this alpha ray source that you are seeing here, few people in few books they claim that Rutherford have used alpha ray source as polonium decay, and few say it was radium decay. So as you can see here, if assuming that this alpha ray source is radium decay, the 226 is the atomic mass, the 88 is the atomic number. Now, when it gets decayed, there would be -4 from here and -2 from here, that leads to radon formation. And similarly, in polonium, there is 210 -4 and 84 -2, that gives you Pb, that is 206 and 82. So this was the alpha ray source, and that was and this were the experimental equations for the alpha ray source as the radioactive materials decay. Now, moving towards the experiment, what were his observations? What were his conclusions? In his experiment, he again used zinc screen to understand the path of this alpha ray. So, when a beam of alpha particles were being hit onto this gold foil, he's had following primary observations. And his observations were the result that led to certain conclusions. So in his observations, he found out, since I said it is one layer of atoms thin, let's just go towards an atom. Let's just see this. Let's just analyze his observation through this. As you can see, most of the alpha ray particles are undeflected, they passed straight through. So observations of Rutherford's alpha ray scattering experiment. His first observation was most of the particles were undeflected. So most particles pass straight with no deflection. His second observation, as you can see here, that only very few particles show a little bit of deflection, that to close from this nucleus. So there is this one particular thing which is called as the nucleus. Coming to that, I'll be coming to that little bit later, but yeah, coming to the second observations, very few particles deflected. Now, so these were the two following observations that he noted. Coming to the third and the very most important observation, that 1 out of 20,000 alpha ray particles, only 1 out of 20,000 alpha ray particles had a straight deflection. So considering this to be the atom and this to be the nucleus, so there was only 1 out of 20,000 that shows a 180-degree deflection. So approx 1 out of 20,000 particle show large deflection around 180 degrees. So that large deflection was seen only in 1 out of 20,000 particles. These were his three most important observations that led him to three important conclusions. Since most of the particles passed through freely without any deflection, his first conclusion can be most of the space in atom is empty. Since very few particles were slightly deviated, the second observation could be there is something positive in the center of atom or at the center of atom. And apart from this two conclusions, his third observation that led to his third conclusion is there is nucleus at center that is positively charged and extremely small compared to size of atom. And so these were his three observations and three conclusions. But there was one thing that you shall remember, that this deflection that happened in 180 degrees, let me clean up. Yeah, so this deflection that you see that have happened around 180 degrees, there is this line that shows a 180 degrees deflection, and that deflection occurs at a certain distance far from the nucleus, and this distance is said to be distance of closest approach. This was one concept that was seen in Rutherford's experiment, where let's say this is the nucleus, this is the alpha ray particle, nucleus, this is the center, and the alpha ray particle reaches to a certain distance but could not collide with the nucleus of the atom, because nucleus is positively charged, alpha ray is positively charged, and after certain point, due to the repulsive deflections of same charges, the alpha ray particle gets at a close proximity to the nucleus and reverts back to its own path around 180 degrees or equal to 180 degrees angle. So I hope you are comfortable. You have understood the Rutherford's atomic model. Now moving towards See, alpha ray scattering experiment is done based on his observations and his conclusions. He have sketched out the atoms, what do you call, he have sketched out this atomic model. So he stated that since nucleus is present at the center, nucleus is present at the center, he have drew a nucleus at the center, and since it is what do you call, since it is very small comparative to the size of atom, he had electrons revolving far from nucleus, and and he stated that electrons revolve around nucleus, and nucleus is very tiny, it is present at the center, and nucleus holds the major weight of atom. But the drawbacks were Rutherford failed to explain how come electrons were revolving around nucleus without getting tired according to classical physics. So Rutherford's drawback was something very interesting, and the person who have overcome that limitation is also very interesting. Now coming to Rutherford's model. So yeah, this model became the basis of our understanding of atomic structure. As I was saying, by Rutherford's model was very interesting. So Rutherford's model, he came up with two things. Nucleus is positive and at center. Second thing, electrons revolve around nucleus. Now, the two things were clear, but it's time to understand the limitation. The limitation of this particular model is the classical physics, and the person who have pointed out this limitation is Maxwell. So Maxwell proposed a particular theory that says okay, the limitation was electrons, how come they revolve without losing energy. So Maxwell is a guy who have pointed out Rutherford's limitation, and it was like boom, all this work, and Rutherford's experiment was pulled down by one single theory. So Maxwell was the guy in classical physics who have brought down this Maxwell's theory, where he says that when we try to read down that theory, we get a conclusion that okay, if electron is revolving around nucleus, how come electron is not getting tired and is not colliding with the nucleus? So electrons, if they continuously revolve, so this is the nucleus and this is the electron. So assuming electron is at this position, electrons upon continuous revolving around the nucleus, they lose energy and they spiral into the nucleus of the atom, disrupting the atom and failing to explain the stability of matter. That was according to classical physics, and that was according to the Maxwell's theory. And for now, resting this case here with a curious question, that how come everything, so much hard work of Rutherford, like student of J.J. Thomson, who was so close to atomic model, who was so accurate with his model, got failed by one classical physicist, that was Maxwell and his theory, Maxwell's theory. And we are going to see who is actually going to save this atomic model. And the secret is Rutherford's student is going to take the entry, and Rutherford's student is going to explain how this particular theory was successfully established. Rutherford's student, that is none other than Niels Bohr, have come out with his own postulate, and Bohr's atomic model, that is the basis of our current model. So it is a great and highly more interesting part in our upcoming session, and in our next class we are going to go through Niels Bohr model of atom. So stay tuned and see you in the next class. Take care. Bye. And I